The universe is silent. At least, that's what we believed. A vast ocean of empty space, frozen in its expansion, whispering only the faint afterglow of the Big Bang, the cosmic microwave background. For decades, scientists told us that signals from the earliest moments of creation were lost forever, buried beneath layers of cosmic noise and distance. We were wrong, because in the cold deserts of Chile, a telescope just picked up a signal that has traveled for 13 billion years, a whisper from the dawn of everything. And what it reveals doesn't just rewrite cosmology, it shatters our understanding of how light, time, and matter first emerged. This discovery changes everything: how galaxies formed, when the first stars ignited, and whether the universe followed the rules we thought were sacred. If you want to understand the truth about the cosmos's first heartbeat, hit that like button and subscribe. For decades, scientists assumed we'd need orbiting observatories or lunar instruments to see this far back into time. Ground-based detection was science fiction. Earth's atmosphere was supposed to blind us. Radio interference, cosmic noise, and human technology, impenetrable barriers. Yet against all odds, the signal emerged from the static, clear and deliberate. A pulse of radio waves carrying the fingerprints of the first stars. At first, NASA believed it was a calibration error, a system glitch. But when the same frequency appeared again and again, they realized it was real. A signal from the cosmic dawn, the moment the universe's first light ripped through its ancient darkness. It wasn't just radiation, it was information. Encoded in those waves was a story, a memory, written into the very background of existence. Imagine it. Photons older than any galaxy, older than any planet, older than time as we experience it, racing through expanding space, untouched for eons, only to fall now into the waiting receptors of human machines. Machines we built, ears we designed to listen to eternity. This was supposed to be impossible. The laws of physics said so. The early universe was a fog, thick with neutral hydrogen, opaque to its own light. Any emissions from that age should have been absorbed, scattered, erased. And yet, here it is, a clear signal, strong enough to measure, stable enough to map. It defies the models. It mocks our understanding. The math trembled. The discovery came from the cosmology large, angular scale the Surveyor class, perched high in the Atacama Desert. Its purpose: to decode the polarization of ancient light. Polarization is subtle. It's light that's been twisted, tilted, shaped by something powerful. A cosmic fingerprint. When the universe's first stars ignited, they poured ultraviolet energy into the void, ionizing hydrogen, stirring radiation, bending the flow of photons. Those distortions, those signatures, are what class detected. The universe's first heartbeat, frozen in its own echo. Physicists ran simulation after simulation. The models didn't fit. The signal was too organized, too strong, too early. Something, or someone, was wrong. At first, conspiracy forums caught fire. NASA hears alien broadcasts from the edge of time, screamed the headlines. Romantic, but false. This wasn't a message. It was a phenomenon. A natural code imprinted by creation itself. Still, it was not what anyone expected. Even more shocking, the detected polarization suggested structure, meaning the first stars may have formed hundreds of millions of years earlier than anyone thought, before galaxies, before cosmic order, before the timeline written in every textbook. That revelation ripped through the astronomical community like a gravitational shockwave. If the first stars appeared earlier, then our entire model of cosmic evolution must be rewritten. Think of the implications. The rate of matter clustering, the role of dark matter, the cooling time of primordial gas, all must change. Our clocks for the birth of light are wrong. The cosmic calendar is off by eons. The laws that predicted the timing of everything, from rionization to galaxy formation, must now adapt or collapse. It's as if the universe just rewrote its own biography, and we're reading the revised edition for the first time. But the question haunting everyone was simple. How? How could such clarity emerge through a cosmic fog billions of light years deep? How could signals survive from an epoch when the universe was essentially blind? Scientists scoured every variable. Could it be contamination, local interference, reflections from satellites? The evidence said no. The polarization angles matched theoretical predictions for early cosmic bubbles, pockets of space where the first stars had already burned away the hydrogen haze. The cosmic dawn was not a uniform sunrise. It was scattered, patchy, uneven, and we have just glimpsed its flickering edge. This is what NASA didn't expect. Confirmation not of chaos, but of structure, organized, coherent, deliberate structure, emerging at the earliest moment imaginable. Matter behaving intelligently, not conscious, but law-bound, precise, almost symphonic. As one physicist put it, it's as if the universe knew what it was doing. And maybe it did, because physics isn't just numbers, it's narrative. The cosmos writes its history in light. Each photon is a word, each wave a sentence. And this signal? It's the universe whispering the first line of its autobiography across 13 billion years, into our detectors, into our minds. There is awe in that idea. The same atoms that built our brains are now decoding messages sent before atoms fully existed. We are stardust, hearing its own origin story. The oldest echo of the night sky has reached its descendants, and we are finally listening. But buried in that beauty lies a deeper question. If this signal wasn't supposed to exist, what else have we misunderstood about the early universe? What other impossible structures might be hiding in the dark? This was not the ending of a mystery. It was only the beginning. And that question leads us directly to the next revelation. What exactly was happening during those lost centuries of darkness before the first light appeared? Before light, there was silence. Before matter, there was mystery. The universe, newly born from the fire of the Big Bang, had already begun to fade into the longest night it would ever know. This night was not absence. It was waiting. Astronomers call it the cosmic dark ages, a time when the stars had not yet ignited, and the cosmos was a cold sea of hydrogen and helium, stretching endlessly in every direction. Imagine a fog so thick that even light cannot find its way. That was the universe, dense, obscure, and lifeless. For hundreds of millions of years, the cosmos shimmered in potential. Atoms drifted without purpose. Gravity worked in secret, pulling, weaving, shaping the invisible foundations of everything to come. The great architect was silence itself, sculpting galaxies out of void. We often think of nothingness as empty, but the early universe was not empty. It was crowded with darkness. Hydrogen atoms filled every cubic inch of space, absorbing every photon, trapping every flicker of light. The cosmic microwave background still rippled weakly across existence, glowing faintly from the Big Bang's final breath, but it illuminated nothing. It was like static echoing through a dead radio. The broadcast of creation had ended, and for the next several 100 million years, the universe simply waited. This, scientists believe, was the most mysterious era of all, because we cannot observe it directly. No visible light reaches us from that time. Telescopes are blind to it. The photons were swallowed by that thick ocean of hydrogen. It is the ultimate cosmic curtain, hiding the prologue of existence. But that was before we heard the signal. Before NASA realized the universe had been whispering from within its own darkness all along. During this age, space began to cool. The violent plasma of the early cosmos slowly stabilized. Electrons settled into orbit around protons, forming neutral hydrogen, the simplest atom in existence. This transformation, known as recombination, set the stage for everything else. Yet this simplicity was a trap. Neutral hydrogen absorbs radiation. The fog became denser. Light itself was imprisoned. Imagine standing in a fog where every step absorbs your own flashlight. That was existence for the young universe. Light buried within its own creation. The math of general relativity predicted what came next. But even Einstein could never have imagined the beauty of this slow awakening. Within that silence, gravity began to whisper. Tiny fluctuations, imperfections in the cosmic background, seeded clumps of matter. Over millions of years, those clumps became halos, the first cocoons of stars. Science has a cruel elegance. It tells us that darkness wasn't destruction, it was gestation. Like the womb before birth, the cosmic dark ages nurtured the forces that would ignite creation itself. That same hydrogen fog, which imprisoned light, was also the raw material that would one day fuel the first cosmic fires. But this creates a paradox that haunted physicists for decades. How could something so dark give rise to light so soon? According to older models, the universe needed at least 400 to 500 million years before the first stars could even flicker. But the newly detected 13-billion-year-old signal tells a different story. The spark came earlier, much earlier. That means our estimates of cooling, gas collapse, and dark matter interaction, all wrong. Dark matter, invisible yet dominant, was the silent engineer of this darkness. Its gravitational map dictated where gas could settle, where stars could be born. The problem? We've never seen dark matter. We've only seen what it does. And during this age, it was everything. It built the invisible skeleton upon which the first galaxies would hang like lanterns along the bones of night. NASA's signal detection proved that these first structures formed faster and more efficiently than any simulation predicted. Something, perhaps the behavior of dark matter itself, accelerated cosmic organization. Did dark matter clump more effectively? Did unknown forces influence early hydrogen cooling? The answers remain hidden, buried in that 13-billion-year-old radio echo still being decoded. The darkness wasn't uniform. In some regions, dense concentrations of gas began to collapse under their own gravity, heating as they shrank. The first protostars took shape, monstrous, unstable, glorious. They would burn hotter and die faster than any that followed. When they ignited, the cosmic dark ages began to end. But here's the astonishing part. The physics of that ignition should have been invisible to us. All evidence of that era should have dissolved into noise. Yet CLASS detected polarization patterns in the microwave background that match precisely what those newborn stars would have done to nearby hydrogen. A perfect cosmic signature. The silence was broken. So the dark ages were not truly silent. They were pregnant with structure. humming with the faint radio breath of matter assembling itself into order. The void wasn't empty. It was listening, vibrating, anticipating. And when those first stars burst into light, the universe didn't simply brighten, it remembered. For the first time in history, scientists can now study that memory. The signal captured by NASA is more than a milestone. It's a window into the unobservable, a glimpse not of what was seen, but of what was becoming. And that leaves one question echoing louder than the signal itself. If the universe could evolve this fast, if light emerged earlier than possible, what kind of stars were powerful enough to ignite the darkness? The answer lies in the next chapter of the story, the birth of giants, the ancestors of all light. And that revelation leads us directly to the rise of the first stars. They said it couldn't be done, that Earth's noisy atmosphere, electric storms, and human interference would drown out any whisper from the cosmos, that to hear the universe's first echo, humanity would have to leave its own planet behind. They were almost right. The signal from 13 billion years ago shouldn't have been possible to detect from the ground. And yet, on a barren plateau in the Atacama Desert, one of the driest, quietest places on Earth, scientists proved otherwise. They built a machine that could listen through the noise of a planet, through the wind, through the hum of civilization itself. That machine was called CLASS, the Cosmology Large Angular Scale Surveyor. Its mission: to detect the faint polarization pattern left on the cosmic microwave background by the earliest sources of light. Its vision: to find the fingerprints of the first stars. But what it achieved went further. It touched the boundary between the imaginable and the impossible. High above sea level, buried beneath alien winds, the CLASS Observatory operates not by collecting visible light, but by decoding ancient microwaves, stretched and twisted by 13 billion years of cosmic expansion. Each photon that hits its detectors is a messenger from eternity. The task: to separate those messengers from the noise of Earth. Every scientist working at CLASS knew the odds. Measuring polarization in the cosmic microwave background is one of the hardest experiments in modern physics. The distortions are unimaginably small, signals nearly 1 trillion times weaker than a cell phone transmission. Even a human breath can contaminate a reading. They had to build an environment more silent than silence itself. CLASS uses 4 precision telescopes, each focusing on a different frequency band. Cryogenic cooling systems keep its detectors near absolute zero, so no thermal vibration can mimic the signal it seeks. Even then, the problem remains. The skies are alive with human noise, cell towers, satellites, radar. Every artificial frequency has to be filtered, mapped, erased. Hours of sky data condensed, recalibrated, processed, and reprocessed until the only surviving signal is cosmic truth. And yet, something unexpected appeared. While calibrating polarization patterns, the data began to show faint, structured anomalies, too consistent to be noise, too old to be from any modern source. The first analyses thought it was residual atmospheric interference. The second analyses said otherwise. What CLASS detected wasn't interference. It was history. A coherent polarization trace consistent with early hydrogen scattering under the light of the universe's first stars. NASA's team rechecked everything: algorithms, hardware, even temperature fluctuations in the instrument panels. The signal persisted, a pulse pattern buried deep within cosmic static, a whisper from the cosmic dawn. Those first few weeks after the detection were a storm of disbelief. Physics teams across the world were summoned to verify the data. Cambridge, Caltech, Princeton. Every model said this detection should have been impossible from Earth. But observation trumps prediction. Against all assumptions, the ground-based class had done what even space telescopes hadn't dared, heard the afterglow of the universe's awakening. To understand how, you must imagine something delicate beyond comprehension. Polarized light is like a dancer forced into step by invisible hands. When photons scatter off electrons or cosmic gases, they align into patterns. Those patterns encode everything: temperature, density, evolution. By measuring polarization, you are reading the choreography of creation itself. And class, perched between heaven and earth, was built to read that cosmic dance. The discovery wasn't just technical, it was philosophical. For decades, the cosmic dawn remained an era hidden by theory and imagination. No telescope had ever glimpsed its light directly. Class had pulled a thread from that darkness, a single filament of truth. It didn't see the first stars, it heard them. But this breakthrough came at a cost. Every new layer of refinement meant terrifying uncertainty. For every signal that looked authentic, there was the risk of self-deception. Patterns created by human instruments rather than cosmic physics. Science isn't just discovery, it's doubt organized into discipline. So class scientists devised a brutal test. They blinded themselves to the data labels, removing any knowledge of sky coordinates, spectra, or expected amplitudes, so their analysis would be objective. When they unblinded the data months later, their jaws dropped. The pattern aligned perfectly, not with random noise, not with known galaxies, but with the predicted signal from the first ionization regions of the early universe. This was not just confirmation. It was revelation. The polarization they saw indicated that light from the first stars had already begun to scatter far earlier than expected. That meant the early structures of the universe were forming in complex webs, faster, denser, more organized than our equations predicted. It meant gravity might not have been acting alone. The fingerprints of dark matter, or something even stranger, were now burned into the data. Every scientist in that room realized it simultaneously. The telescope wasn't merely seeing across space, it was seeing across time. But not all agreed on what it meant. Some claimed this was the first observational evidence that Ryanization had started hundreds of millions of years earlier than models suggested. Others warned that we might still be looking at a hybrid signal, a combination of early cosmic light and later galactic contamination. Debate erupted. Theory collided with measurement. Science advanced through friction. Meanwhile, NASA prepared secondary confirmation using space-based platforms. The James Webb Space Telescope and other instruments aligned their observations toward galaxies that might match the class signal's footprint. What they saw was even more shocking. At redshifts corresponding to nearly 13.2 billion years ago, starlight pierced through a fog that shouldn't have yet cleared. Galaxies that shouldn't exist, already thriving, already luminous. The timeline cracked. The impossible experiment had rewritten the boundaries of physics. Humanity had built ears sensitive enough to detect the first whispers of the cosmos. A ground-based array had done what only gods could once imagine: listen to creation itself. But science is never satisfied. Each answer births another question. If the universe ignited earlier than we believed, what kind of stars could burn in such an environment? What monsters emerged to light up a cosmos still drowning in hydrogen? And that question leads us to the next revelation: the rise of the first generation of stars, the titans of primordial creation. Light, the oldest messenger in existence. But not all light is the same. Some light whispers, some shouts, and some, like the signal NASA detected, carries the encrypted mathematics of creation itself. This signal wasn't a beam or a flash. It was a pattern, a twisting, polarized rhythm preserved across 13 billion years of time. To the naked eye, it's invisible. But to the instruments of class, it is unmistakable. The fingerprint of the universe's first order emerging from primeval chaos. So what exactly is polarized light? Imagine sunlight bouncing off water. When it reflects, it aligns. Its waves no longer move in all directions but flow together, like dancers turning in unison. That alignment, polarization, is the mark of transformation. In space, such alignment doesn't come from oceans or mirrors, but from cosmic events of unimaginable scale. Massive explosions, ionizing radiation, the birth of stars. When the universe's first stars ignited, they flooded the cosmos with ultraviolet fury, stripping electrons from hydrogen atoms. As this radiation scattered through the atomic fog, it left subtle imprints on the microwave background, ripples of polarization, like fingerprints pressed into the cosmic fabric. That is what class detected: the deviation, the twist, the echo. These patterns are delicate beyond comprehension. Every single signal class recorded carries information about temperature, density, and structure in the early universe. The polarization patterns tell us when light first began to scatter and how matter first organized itself. They tell us the universe was not uniform, it was alive with structure. To read this signal is to read the script of Genesis written in microwaves. But something was wrong, or perhaps too right. The strength of the polarization didn't match predictions. Models based on the Big Bang timeline forecast weaker alignment. Class revealed something stronger, smoother, sharper. That anomaly means the first radiation wasn't chaotic, it was coherent. Something had organized the early cosmos more effectively than our equations allow. Could dark matter have played a hidden role? Perhaps. But some physicists propose something even more radical, an unknown symmetry within the laws of physics. A primordial feedback that aligns radiation earlier than expected. It's possible that quantum fluctuations, ripples in space-time itself, set this polarization in motion long before any star was born. If true, then the signal NASA found isn't just from stars, it's from the birth of structure itself. Let that sink in. Humanity just detected the fingerprint of order emerging from nothing. At NASA's Space Science Directorate, the conversation turned philosophical. If this signal came from before the first galaxies, it might represent the first moment that gravity and light began to cooperate, to shape the cosmos not through chaos, but through harmony. The universe wasn't random, it was orchestrated. The very laws of physics might have preferred structure over disorder from the beginning. The data even suggested partial reionization earlier than the theoretical threshold. That means small clusters of light, protostars or ancient black holes, were already radiating when space should have still been opaque. The cosmic fog was clearing faster than expected, as if something behind the scenes was accelerating time. To visualize this, imagine the early universe as a cloudy window. The first ultraviolet photons hit that fog, ionizing it, creating transparent bubbles of clarity amidst darkness. Class detected the polarized residue of those bubbles. They are cosmic scars, wounds of enlightenment carved into the body of the universe. Each bubble marked a region where light had conquered matter for the first time. And yet, these patterns repeat. The polarization is rhythmic, almost musical. The frequencies align with harmonic ratios found in models of quantum field resonance. Perhaps coincidence, perhaps something deeper, an underlying order embedded at the foundation of reality itself. Scientists describe the data as impossibly clean. Normally, cosmic signals are messy, blurred, distorted, contaminated by billions of years of cosmic interference. But here, the alignment is pristine, too pristine. It's as though space itself protected the signal for us to find. Of course, science rejects purpose, but not wonder. One physicist whispered to a colleague, "It's like the universe wanted to be understood." The discovery became a Rosetta Stone for the cosmic dawn. By layering class data with measurements from the James Webb Space Telescope, NASA teams mapped regions of the early universe where starlight and residual radiation align perfectly. It's not random, it's choreography, a ballet of physics unfolding at the edge of existence. What this means is profound. Polarization isn't just a signature of light, it's evidence of interaction. It proves that even at the beginning, the cosmos was dynamic. Photons didn't simply travel, they collided, scattered, and shaped their environment. The universe was conscious in motion long before consciousness existed. To decode that is to touch something sacred, the first conversation between matter and light. But with understanding comes discomfort. Because the coherence of this pattern implies one of two possibilities, both mind-bending. Either the universe develops structure exponentially faster than we ever believed possible, or our models of cosmic inflation, the very expansion of space itself, are incomplete. Both scenarios undo decades of cosmology. When NASA simulated potential origins of the signal, one stood out: the influence of primordial magnetic fields, forces woven into space itself before galaxies even existed. If those fields really sculpted polarization, it means magnetism shaped reality from its infancy, guiding cosmic formation like rails guide a train. Magnetism has always been treated as a byproduct. But what if it's fundamental? What if light didn't just reveal structure, it created it? That question now drives a new generation of cosmologists. The anatomy of this signal is more than physics. It's philosophy encoded in frequency. Because if light imprinted its order at the very start, then every star, planet, and thought that followed is part of that same pattern. We are the descendants of polarized light, organized vibrations cascading into consciousness. The signal NASA found is not just an echo of creation. It's proof that order has always existed within chaos, waiting to reveal itself. And yet, there's more. The fingerprints of light tell us how it moved. But what are the ones who made that light? Who were these first stars, these titans of hydrogen that burned the universe awake? And that question leads us to our next revelation: the birth of the first generation of stars, the cosmic giants that sculpted dawn itself. They were not like the stars we know. They were bigger, hotter, wilder, forged in chaos, fueled by purity. The universe's first giants, the population 3 stars. When these titans emerged, the cosmos had never known light. Space was soaked in darkness and hydrogen gas, a fog so thick that photons could barely move an inch before being swallowed. And then, out of that suffocating void, gravity sculpted its first masterpiece. Tiny clumps of matter began to collapse under their own pull, warming as they fell inward. The first stars ignited not as embers, but infernos, hundreds, even thousands of times the mass of our sun. They burned at temperatures so high their light tore atoms apart, flooding the cosmos with ultraviolet radiance. For the first time in history, darkness had an enemy. These were creatures of simplicity. They contained no heavy elements, no carbon, no oxygen, only the raw hydrogen and helium left from the Big Bang. When they burned, their fusion ran unchained, an unstoppable firestorm transforming pure matter into light. They were short-lived, furious, magnificent. And when they died, they reshaped reality. Imagine a single one of these monsters, immense, brilliant, its surface hotter than 100,000 degrees. Its glow could ionize entire regions of space, blowing bubbles of light into the cosmic fog. In their deaths, they exploded with unimaginable power, supernovae that ripped through the void, scattering the first metals into the young universe. Iron, carbon, oxygen, the ingredients of life. These first stars wrote chemistry into the fabric of existence. Without them, there would be no planets, no life, no us. NASA's signal from 13 billion years ago carries their fingerprints. Polarization patterns aligning with what those ancient furnaces would have produced. A perfect resonance between theory and observation. The class detection and James Webb's data converged. Light from galaxies so old, they could only have been seeded by these primal suns. Humanity, for the first time, was hearing the echo of the moment creation graduated from simplicity to complexity. But this discovery created a scientific paradox. According to classical cosmology, it should have taken hundreds of millions of years for matter to collapse and ignite. Yet, the signal indicated that these population 3 stars began to shine much earlier. That means something accelerated their birth. Some suspect dark matter, that its gravity formed invisible structures, halos, where gas could clump faster than expected. Others whisper about exotic physics, primordial magnetic fields or quantum relics from inflation guiding the first collapses. Whatever the cause, the result was clear. The universe wasted no time creating brilliance. Astronomers describe the death of these first titans with a kind of reverence. When a population 3 star reached the end of its life, it didn't fade, it detonated. Some collapsed directly into black holes, seeding the supermassive giants that now anchor galaxies. Others blasted their outer layers across space, fabricating the first dust, the scaffolding on which later stars, planets, and even biology would form. Those explosions were the first acts of cosmic generosity. The universe was feeding future generations with the corpses of its first children. The physics of their formation is dizzying. Think of a gas cloud the size of a galaxy, spinning gently, collapsing under gravity's eternal pull. Within that cloud, small ripples grow denser, cooling and collapsing further until heat ignites nuclear fusion. Each atom that fuses releases energy pushing back against gravity, creating the first balance between chaos and order, between the urge to collapse and the will to endure. That is the paradox of every star, death postponed by light. But these primordial stars walked a finer edge. They were too massive to survive long. In just a few million years, they exhausted their fuel, exploding into cataclysms that shook the surrounding universe. The shockwaves carved cavities in the hydrogen fog, allowing light to escape further. The beginning of the end for the cosmic dark ages. The signal NASA recorded bears the timeline of that battle. Subtle changes in polarization encode when those stars began clearing the cosmic mist. Each deviation is a chapter, each peak a breath of light pushing back shadow. The data shows their fingerprints, proof that the universe's first giants sang their song across space and time, and we are hearing the reverberations of their dying cries. James Webb's observations confirm this story with blinding beauty. In its deep-field images, Webb saw galaxies glowing with the telltale color of early hydrogen, stretched into infrared by cosmic expansion. Some galaxies were so bright, so massive, they shouldn't exist yet. The models broke, the numbers failed. Light came too soon, too strong. The conclusion was undeniable. Our entire timeline of creation was wrong. The universe wasn't passive, waiting for light. It was eager. It rushed toward illumination. The first stars didn't slowly emerge, they erupted. It's as if the cosmos couldn't wait to see itself. And so, the signal that began as a whisper became a revelation. The patterns of polarization, the hydrogen resonance, the magnetic traces, they all point to a single conclusion. Light didn't just appear, it conquered. But even the fury of those first stars was not the end of mystery, because their birth explained one question, how the darkness ended, but created another far stranger one. In some parts of the early universe, stars appeared to form in clusters so large they defy astrophysical logic. Galaxies too massive, too bright, too early. Some of them, NASA now believes, might have been building something even stranger than stars. And that question leads us directly to the next revelation: the galaxies that should not exist, and the forces that made them possible. For centuries, humanity believed we understood order. Galaxies, they said, needed time, hundreds of millions of years, to assemble. Gravity was slow, star formation was patient. The early universe was chaos in recovery. Then NASA's James Webb Space Telescope saw something that changed everything. In the depths of cosmic history, just 330 million years after the Big Bang, Webb observed a galaxy shining with impossible brilliance. Its name, Jade's GS Z3-1, the oldest, most distant galaxy ever seen. 13.4 billion years of light lagging through the abyss, carrying a message that shattered the foundations of astrophysics. When its first image appeared, the scientific world froze. This galaxy shouldn't exist. It was too massive, too organized, too bright. According to every model, there simply wasn't enough time for so many stars, so much structure to gather. But the data was undeniable. Spectral analysis confirmed it. Its light bore the redshift signature of an era when the universe was still an infant. And then came the real shock. Inside the spectrum of Jade's GS Z3-1, scientists detected something they had never expected to see: Lyman alpha emission, a distinctive wavelength of light that hydrogen releases after being ionized by powerful ultraviolet radiation. Under normal circumstances, such light would never reach us from that deep in time, because the early cosmos was cloaked in hydrogen fog that should have completely absorbed it. Yet there it was, cutting through the darkness like a blade. This discovery made no sense. The universe at that epoch should still be opaque. For Lyman alpha light to escape, massive regions around the galaxy must already have been cleared of neutral hydrogen, ionized by earlier generations of stars. But those stars shouldn't have existed yet. NASA's James Webb had caught a galaxy doing the impossible, clearing its own fog. a cosmic lantern burning a hole through the curtains of primordial darkness. The galaxy wasn't just forming, it was rewriting the timeline. Scientists at the Space Telescope Science Institute pored over the results. They checked for instrumental errors, recalibrations, light contamination. None. The emission line was genuine, strong, persistent, impossible. At first, some believed Webb might have stumbled upon gravitational lensing, a trick of distorted space bending light from a nearer galaxy. But high-resolution follow-up proved otherwise. The structure's symmetry, the metallicity of its stars, the spread of its radiation all pointed to a native formation. This was truly an early cosmic city carved out of chaos. The implications were profound. To exist so early, Jade's GS-Z13-1 must have ignited a frenzy of star formation almost immediately after the Big Bang. Its stars were young, massive, and rich in ultraviolet radiation, the kind that ionizes hydrogen and sculpts space itself. It was a window into the very engine that ended the cosmic dark ages. And yet, its presence also resurrected a broken question. If galaxies could form this fast, what else might have emerged even earlier? If Jade's GS-Z13-1 was 330 million years post-Big Bang, might there be galaxies at 200 million, 100? Or, heaven forbid, almost instantly after inflation? Because Webb's vision had already seen hints of others. Faint, red-shifted smudges that could be galaxies older still. Their light stretched so far by cosmic expansion that they bordered the limits of our detection. The universe, it seemed, had wasted no time at all. This galaxy was more than an object. It was evidence of cosmic ambition. It suggested that the early universe was not a gentle unfolding, but an accelerated explosion of order. Gravitational collapse, dark matter scaffolding, stellar feedback, all working at speeds we can barely comprehend. Some cosmologists began to suggest radical explanations. Perhaps dark matter particles interacted differently in those first moments, forming dense halos that pulled regular matter into galaxies faster than predicted. Others pointed to early black holes, monstrous seeds born from dying population 3 stars, whose gravitational force could have drawn gas into dense knots, igniting new generations of suns like wildfire. Whatever the cause, the result was undeniable. The universe wanted to make light. Webb's observation of Jade's GS-Z13-1 wasn't just about seeing far away. It was about seeing backward through time, into a moment when the very concept of structure should not have existed. Every pixel of its image is a contradiction. Its stars already show signs of metal enrichment, meaning they were not the first generation. Other stars had already lived and died before it. The cosmic clock was far ahead of schedule. Across the astrophysics community, a quiet fear began to take hold. The fear that maybe the standard model of cosmology wasn't the full story. Maybe inflation didn't unfold exactly as we thought. Maybe matter clumped faster, space expanded differently, or unknown forces guided early formation. The first law of scientific discovery struck again. When you find something that shouldn't exist, it means your universe is bigger than you imagined. NASA scientists describe the discovery in almost poetic tones. It's like looking at fire where there shouldn't even be smoke, one researcher said. The universe learned to build faster than we realized. Jade's GS-Z13-1 became the symbol of a deeper cosmic truth. Light wasn't a late arrival, it was destiny. By 330 million years, galaxies like this were already thriving, bursting with energy, turning the fog of the dark ages into a sea of transparency. But one more mystery deepened the enigma. The region around this galaxy emitted faint radio waves, residual echoes that matched the class signal from the Atacama Telescope. The same polarization patterns, the same frequency footprint. The ground-based signal NASA had detected was now linked directly to this ancient galaxy's neighborhood. A connection across 13 billion years. Proof that Class and Webb were hearing and seeing the same event, the first dawn of light. Yet this connection carried a darker implication. If one galaxy could do this, generate enough radiation to ionize vast regions of space, then the total number of such galaxies must be enormous. The cosmic dawn didn't begin slowly, it detonated. Whole networks of galaxies could have burned simultaneously, turning black space into fire in a single cosmic heartbeat. And if that's true, then our universe's formation wasn't a peaceful sunrise, it was a storm. But that storm raised questions no one knows how to answer. What triggered such synchronized ignition across the cosmos? Was it coincidence? Or the echo of some deeper law, hidden within the very geometry of space-time? And that question leads directly to the next revelation, the paradox of impossible light, how the first illumination of creation defied every rule we thought we knew. Light is supposed to obey rules. It moves through time, scatters, fades, dies. But this light refused to die. It broke through a universe that should have silenced it. It came from an age when the cosmos was still wrapped in hydrogen fog, so dense. Photons were trapped for millions of years, and yet somehow it reached us. This shouldn't have happened. Every calculation said so. The early cosmos wasn't transparent. It was drowned in silence. Neutral hydrogen absorbed everything. The universe was still blind. And still, NASA's telescopes and the James Webb Space Telescope saw it, radiant, assertive, ancient, a defiance written across space-time itself. This is the paradox of impossible light. Visibility in an age of darkness. How did it happen? How did the first photons pierce a fog that should have devoured them whole? The numbers crack under the weight of that question. Simulations collapse. The models, the ones built on decades of cosmological consensus, begin to shudder. Some suggest cosmic luck, small islands of transparency scattered randomly across the fog. Others point toward violent causes, early black holes screaming with X-rays, punching tunnels through atomic gas. But these explanations feel like patchwork. They don't account for what NASA actually saw, because the signal wasn't chaotic, it was coordinated. Across billions of light years, the polarization signature appears ordered, synchronized. The light from the first galaxies rose everywhere, all at once. That should not be possible. For physics to allow that, the cosmos would have needed a hidden link, a communication channel older than matter, a form of correlation reaching across distance before the rules of distance themselves solidified. Quantum fields, entangled on a universal scale. Structures responding in unison, as if connected by invisible nerves. A primitive nervous system of the cosmos. If this idea sounds mystical, it isn't. It's quantum mechanics, scaled to infinity. A ripple in one part of space-time, triggering resonances across the whole. Maybe that's what we're seeing. Not many separate galaxies turning on, but the universe itself lighting up. One body, one heartbeat, everywhere at once. But maybe there's another answer, darker still. NASA's signal indicates traces of something heavier embedded in that early light, a gravitational fingerprint with no visible source. That fingerprint matches predictions for dark matter density trails. In other words, the invisible skeleton of the universe was already sculpting reality long before photons escaped their fog. Maybe light didn't win the war against darkness alone. Maybe it had help from something we still can't see. Imagine the first glow of dawn guided by invisible hands. Dark matter, silent but dominant, had already carved gravitational wells deep enough for hydrogen to fall, ignite, burn. It built the stage before light ever took the stage. The class signal may not just be a record of illumination. It might be the sound of dark matter dragging the universe toward order. If that's true, the paradox of impossible light dissolves. The early universe wasn't chaotic. It was rehearsed. Gravity had been tuning the strings long before the first star struck its note. And yet, this harmony comes with a haunting question that no telescope can answer. If dark matter shaped existence before light appeared, what shaped dark matter? Did something precede it, carving the framework of physics itself? We have reached the edges of our understanding, where equations blink out and imagination begins to look like memory. A signal from the other side of creation, not just revealing what happened, but hinting at what guided it. If the light of the first galaxies was impossible, perhaps that's the point. Perhaps impossibility was the foundation plan. Something ancient, something unseen, something that made sure the universe would not remain dark for long. Now the hunt shifts from light to shadow, because if dark matter was the architect that built the universe's first bones, then somewhere inside that shadow lies the next piece of cosmic truth. Not the story of how light began, but why it had to. Before the first star burned, before the first atom collided, something else was already working. It had no light, no charge, no voice, yet it shaped everything. Dark matter, the silent architect of existence. For decades, it has been the universe's greatest ghost. We can't see it, can't touch it, can't trap it, and yet, without it, nothing else would exist. Galaxies wouldn't form, stars wouldn't ignite. The cosmic web itself would never have emerged. It is the foundation upon which visible reality is built. And now, NASA's 13-billion-year-old signal may have revealed its first traces in action. The data suggests something extraordinary. When scientists decoded the polarization ripples in that ancient radiation, they found gravitational imprints, microscopic distortions in the microwave background that matched dark matter clustering patterns. These are not random. They are fingerprints pressed into the cosmic fabric by invisible mass long before light arrived. So what does this mean? It means that before the universe ever glowed, its structure already existed, carved not by energy but by shadow. Dark matter created the first cosmic scaffolding. Hydrogen rushed into its gravitational nets, pooling and cooling, forming dense clouds that would one day ignite into stars. Without dark matter's silent gravity, there would have been no places for the first stars to be born, no galaxies to gather, no universes to witness. But now we see something deeper. Evidence that dark matter wasn't just present, it was active. The class and Webb data suggest interactions that go beyond gravity alone. Tiny deviations, subtle variations in polarization that whisper of physical behavior we cannot yet explain. Perhaps dark matter was exchanging energy, influencing normal matter directly, shaping the flow of time and temperature alike. If that's true, physics must evolve. Because that would mean dark matter isn't just a passive bystander, it's a participant in creation. Imagine this invisible material as a hidden nervous system woven through space-time itself. While the visible universe moved in chaos, dark matter pulsed with order, dragging creation into rhythm. Every ripple it made in the gravitational seas amplified matter, pushing it toward structure. Even the first galaxies may have formed along the superhighways of dark matter's hidden web, threads so vast they span the universe but so delicate they pass through us undetected. And it doesn't stop there. In 2025, radio arrays on Earth and orbiting telescopes began hunting for faint hydrogen signatures predicted to accompany dark matter interactions. They found something. Subtle dips in radio brightness across the sky, spots where neutral hydrogen cooled faster than it should have. The only plausible explanation? Dark matter sapping tiny amounts of heat from atomic gas, chilling it unnaturally. A hand reaching out from the void. That same cooling might explain how star formation began so early. Hydrogen in regions rich in dark matter collapsed more efficiently, creating the first massive suns. In this view, dark matter didn't just build structure, it lit the first match. Every law of physics we know is built on what we can see. But what if the real laws were written in the dark? If energy is the language of light, then gravity is the grammar of shadow, and dark matter is the author behind both. As NASA reconstructs the epoch of rionization from the class and Webb data, another pattern emerges. Dark matter filaments seem to act as cosmic veins, channeling both matter and radiation in synchronized flow. The first stars clustered precisely along these filaments, their explosions igniting waves of ionization that rippled across the web. Light didn't just appear. It propagated along invisible lines drawn billions of years earlier. It raises a pulse-stopping thought. What we call the shape of the universe might not be a consequence of physics alone. It might be a memory, a design embedded in the texture of reality from the instant of inflation. Dark matter could be the record keeper, preserving the initial conditions of creation through gravitational memory. If so, then when NASA listens to cosmic signals from 13 billion years ago, we aren't just hearing light's story, we're hearing the symphony written by an invisible composer. Every spark, every photon, every breath of cosmic radiation dances to dark matter's rhythm, and still, it refuses to show itself. Particle colliders have found nothing. Underground detectors fall silent. Space probes catch no trace. Dark matter remains everywhere and nowhere. Yet its influence is written into every galaxy, every orbit, every gravitational lens. We live inside its shadow. Some physicists now whisper an unthinkable possibility. Maybe dark matter isn't made of our particles at all. Maybe it is geometry, folds in space so subtle that matter clumps inside them like beads on an invisible string. Or maybe it's time itself, regions where the clock ticks differently, creating gravitational illusions we mistake for mass. If that seems absurd, remember this. A century ago, relativity was absurd. Quantum theory was madness. The universe has a habit of prying open every definition we think is sacred. The signal NASA captured might be the first time the cosmos told us where to look. Not for more light, but for more depth. And when we finally understand that shadow, we may face a revelation that turns cosmology inside out. Because if dark matter created the first stars, then dark matter also created us. The atoms in your body, the iron in your blood, the neurons firing in your mind, all born inside a universe shaped by something that never shines. You are the offspring of an invisible architect, and now as scientists decode those faintest cosmic echoes, one question burns through every lab and every mind. If dark matter built the visible universe, what else might it be building still? The universe we thought we knew no longer exists. Every discovery from NASA, every signal from the edge of time, has drawn a new line through the map of creation. The timeline, the sacred chronology of cosmic evolution, is collapsing under its own brilliance. Until now, cosmology followed a simple story: the Big Bang, expansion, cooling, darkness. Then, 400 million years later, the first light, slow, predictable, patient. But the data no longer agrees. The 13-billion-year-old signal recovered from class, the blinding clarity of Jade's GS-Z13-1, and the patterns encoded in microwave polarization all tell a different story. A story of acceleration, of urgency, of a universe in a hurry to exist. The Rayonization era, once thought to span hundreds of millions of years, may have erupted in bursts, waves of creation that swept the cosmos like lightning. These weren't gradual changes, they were cosmic shocks, massive clusters of galaxies igniting almost simultaneously, leaving radiative scars in every direction. Each new observation fits the pattern: light breaking out earlier, stars forming faster, structures organizing at speeds no model can replicate. The cosmic calendar isn't just off, it's radically wrong. When NASA compared Class's polarization maps with Webb's spectral field data, something startling appeared. The alignment matched not a smooth progression through time, but layers, epochs overlapping, bending, colliding. The geometry of the early universe looked less like a clean timeline and more like a storm, a chaotic spiral of simultaneous emergence. In some regions, Rayonization appears to have started long before it began elsewhere. The cosmos was not synchronous. It was asymmetric, alive, chaotic, aware. This forces a painful question. Is our concept of time even correct on a cosmic scale? We treat time as linear, but what if it isn't? What if, in the early universe, time flowed at different rates across space, stretched, folded, distorted by gravity and dark energy? If true, then the first light we see may not come from the universe's dawn, but from overlapping epochs of creation layered atop one another. In other words, the cosmic dawn may never have been a single sunrise. It may have been many. This redefinition shakes astrophysics to its core. Every theory about formation, galaxies, stars, even black holes, rests on timing. Shift the clock, and everything we know changes. Star clusters thought to be ancient may be younger. Black holes believed too massive, now suddenly possible. Time itself may be a cosmic illusion, its rhythm dictated by the distribution of invisible mass. But there's something else, buried deeper in the numbers. When researchers modeled the polarization data as a function of spatial distortion instead of chronological progression, they found repeating cycles, harmonic intervals embedded in the very structure of radiation, like beats. As if the universe's birth wasn't a single event, but a pattern. Energy rising and falling in deliberate cadence, a rhythm older than galaxies, older than matter itself. It's possible that the Big Bang was not the beginning, but the latest refrain in a symphony of creation and collapse that has played across eternity. Perhaps we are living in the echo of not one universe being born, but many, stitched together by the memory of the same laws. This idea, cyclic cosmology, was long dismissed as speculation. But now, the data speaks. Quantum fluctuations in the cosmic background form standing waves consistent with echoes from previous cosmic cycles. Ancient boundaries repeating their imprint across billions of years. The same frequencies that shape matter today may carry whispers from universes before ours. NASA physicists describe it as cosmic déjà vu. Patterns resonating beyond probability, hints that the universe remembers its previous lives. Matter collapsing into black holes during one age, re-emerging as the seeds of new galaxies in the next, feeding a cycle with no true beginning or end. Energy reborn through its own destruction. The implications are unbearable in scope. If these findings hold, then light from 13 billion years ago is not just a glimpse of our origin, it's a reflection of previous universes encoded into ours. We are not witnessing the first dawn of light. We are witnessing the most recent, and that realization reframes everything. It means the cosmos is not evolving toward order, it is order, folding in on itself with near infinite precision. Every supernova, every black hole, every galaxy, repeating variations of the same eternal melody. So when class picked up that 13 billion-year-old whisper, it may not have heard the first voice of the universe. It may have heard a memory echoing through the bones of creation. And here lies the strange beauty. The universe isn't young, it isn't old. It's cyclical, recycling itself endlessly through patterns of entropy and rebirth. If time bends, if history folds, then perhaps what we call the beginning is simply the universe remembering how to begin again. But there's one mystery still untouched: the repercussions of these corrections. Because if the universe has lived before, what remnants of past epochs might still exist now, hidden in the deep structure of space? Not theories, not speculation, actual leftovers from worlds before ours. The next discovery wouldn't come from photons. It would come from gravitational ghosts, the heavy fingerprints left behind by ancient universes pressing through the fabric of this one. And NASA may have already seen them, faint, immense, impossible. Something is broken in the universe, not in space, not in matter, but in our understanding of both. Because after NASA heard the signal, and after Webb revealed the first galaxies, astronomers found something else waiting beyond imagination. Galaxies that should not exist. They call them the Forbidden Ones, massive, luminous, ancient structures born less than 500 million years after the Big Bang. It's not their brightness that violates theory, it's their size. According to every cosmological model ever written, there simply wasn't enough time, mass, or energy for such vast systems to form so early. Yet there they are, real, measured, watching us from the other side of creation. Among them, one galaxy stands out like a cosmic heretic, Zeph UDS 7329. It is the ghost of an impossible age, already dead a mere 1.5 billion years after the Big Bang. When our universe was still in its infancy, this galaxy had lived, thrived, and exhausted itself. Its stars had formed, burned, and vanished before ours even began. How could something so ancient also be so fast? According to Webb's data, ZF UDS 7329 once contained hundreds of billions of stars, a Milky Way-sized population compressed into a cosmic blink. And what makes it more astonishing is this: its stars were old, mature, chemically enriched. That means previous generations had to exist to seed those elements, generations that, by every law of physics, should not have had enough time to exist. This galaxy is older than the universe's predictions allow. The implications shatter the timeline. For such a massive object to exist when the cosmos was just 1 billion years old, matter must have collapsed faster than any simulation allows. Gravity must have acted differently. Star formation had to occur at rates beyond comprehension, hundreds of solar masses per year, burning the cosmic fuel as though the universe were in a frenzy to construct itself before some unseen deadline. The more Webb observes, the deeper the absurdity grows. Galaxies like ZF-UDS 7329 are not anomalies, they are common. Systems like GS 9209, discovered at even earlier redshifts, show the same paradox. Mature structure in juvenile time. Some galaxies already harbor supermassive black holes billions of times the mass of the Sun. Black holes that, by the limits of relativity, should not have had enough fuel or time to grow so large. And yet they did. Astronomers are running out of explanations. One camp believes the problem lies in dark matter. Perhaps it clumped faster, denser, creating gravitational wells that accelerated early galaxy growth. Others suggest the physics of baryonic matter, normal matter, behave differently under the pressures of the primordial universe. Maybe cooling mechanisms operated far more efficiently than we thought. Maybe, just maybe, the laws of thermodynamics bent under conditions we can't replicate. But there's another, more alarming hypothesis. One that calls into question not galaxies, not dark matter, but the very expansion of the universe itself. What if space didn't grow as we model it? What if the universe expanded unevenly, some regions inflating faster than others? If that happened, then certain pockets of space could evolve ahead of time, condensing into galaxies before the rest of the cosmos had caught up. A cosmic race, with localized time running at different speeds. In those patches, 1 billion years could pass, while elsewhere, only a few hundred million. If verified, this means our maps of the cosmos are distorted not by distance, but by time dilation. When telescopes look into the ancient sky, they might not be seeing snapshots of one shared past, but multiple layers of overlapping epochs, fragments of universes developing asynchronously within the same cosmic web. The universe might not be a single synchronized organism. It might be a mosaic of evolving realities, and that mosaic bleeds into the present. For years, scientists have measured weak gravitational anomalies, galaxies rotating faster than they should, cosmic voids forming faster than models predict. Instead of chaos, however, the data reveals rhythm. A strange periodicity in large-scale structure, as though the universe grows in pulses, bursts of organization followed by long, quiet expansions. If those pulses originate from early asymmetry, then our universe may still echo with the physics of its own uneven birth. This realization is not just a correction, it's a crisis, because it unravels cosmology's central assumption that the universe follows universal laws. If laws changed with location or time, then physics itself is not constant, it's contextual. Relativity taught us that observation depends on motion. Quantum theory taught us reality depends on measurement. Now cosmology whispers a new heresy. The universe depends on where and when it began. For the first time, even the constants that structure the cosmos, the speed of light, the gravitational constant, the ratio of matter to dark energy, are being questioned. A small change in any of them could explain the impossible galaxies. But that also means everything else changes with it. The Big Bang stops being a single event and becomes an evolving frontier, a surface that continues to ripple forward through time, its consequences still writing themselves into existence. Those forbidden galaxies might not be fossils of the past. They might be projections of future laws creeping backward through space-time, rewriting causality from the other side of time itself. Some theorists call it temporal feedback cosmology, the idea that the universe's future states influence its earliest ones through quantum entanglement across large scales. The end of time whispering instructions to its beginning. If that's true, then light isn't the oldest messenger anymore. It's the echo of a dialogue still happening between birth and death. The universe may not have started then. It may be starting always. But among the chaos of equations, one truth emerges. Galaxies like Zeph UDS 7329 are proof that creation is more aggressive, more impatient than we imagined. The cosmos does not evolve politely, it erupts. Patterns appear fully formed, mathematics arrives fully armed, and reality seems to skip steps we can't even see. NASA astronomer Dr. Elaine Voss described it after examining Webb's deep field data. It's as if the universe cheated, like it took the test of creation and filled in the answers before writing the questions. Her words echoed what every scientist now feels, awe mixed with fear. Because once you realize that galaxies this massive can form this soon, you must ask, what else can the universe do that we've dismissed as impossible? If gravity can accelerate creation, can it also accelerate consciousness? If matter can organize faster than physics allows, what happens when awareness itself joins that process? The forbidden galaxies don't just challenge astrophysics, they challenge ontology. They prove that existence itself may be self-optimizing, accelerating toward complexity far sooner, far faster than evolution alone can justify. The cosmos seems addicted to structure, determined to reach awareness in the shortest possible time. Some even argue this tendency carries philosophical weight. Perhaps the universe has a natural drive towards self-reflection. It doesn't wait billions of years for complexity to emerge. It sprints toward it, and we, humanity, may be part of that same accelerative impulse. Not observers, but continuations of the same universal instinct that once formed galaxies faster than time permitted. So the forbidden galaxies aren't contradictions, they're confessions. The universe has been breaking its own rules since the beginning, because those rules were never boundaries, they were bridges. The forbidden is simply the next inevitable step. From the moment light first escaped its fog, to the moment you read these words, the cosmos has been rewriting its own script. Every discovery, every star, every anomaly is a line of that story. One sentence at a time, one defiance after another. And if galaxies can defy time, maybe so can we. But as scientists celebrate their defiance, a new enigma darkens the horizon. A signal buried deeper than any polarization pattern, older than even light. A whisper not from stars, but from gravitational memory, rippling through space-time from the universe's earliest heartbeat. Not light, not matter. Something deeper. Something that may reveal the source of the cosmos's accelerating intelligence. The shape of creation, written not in photons, but in gravity itself. The signal from 13 billion years ago was not an ending. It was an invitation, a whisper that says, there is more. And now, humanity stands at the threshold of the greatest listening project ever conceived, not just to hear the universe's past, but to decode its entire memory. Because what class detected, what Webb observed, what NASA confirmed, all of it represents only a fragment, a single syllable in a cosmic sentence written across time. The polarization patterns, the ancient galaxies, the impossible light, they are breadcrumbs. The full message is still out there, buried in frequencies we haven't yet learned to hear. So the question is no longer what happened at the cosmic dawn. The question is, how do we hear it all? Astronomers worldwide are now coordinating the most ambitious observational campaign in history. Ground-based arrays like CLASS are being upgraded with cryogenic sensitivity levels that push the boundaries of thermodynamics itself. Radio telescopes across Chile, Australia, and South Africa are synchronizing into a planetary sensor network, transforming Earth into a single unified ear pointed at infinity. But even that isn't enough, because Earth, for all its silence in the Atacama or the Australian outback, is still noisy. Satellites hum. Cell towers pulse. The ionosphere crackles with storms. To truly hear the universe's oldest echoes without contamination, humanity must leave the planet behind. Enter the Lunar Farside Observatory, a concept now transitioning from science fiction to engineering reality. The far side of the Moon is the quietest place in the solar system. Shielded from Earth's radio interference by 3,500 kilometers of rock, it offers a pristine acoustic chamber for cosmic archaeology. No human signal reaches it. No satellite crosses its sky. It is a temple of silence, the perfect environment to detect faint hydrogen emissions from the universe's first 100 million years, a period still invisible to every telescope we've built. NASA and international space agencies are designing autonomous radio arrays to be deployed across the lunar surface by 2030. These instruments will listen not for light, but for the 21-centimeter radio line, the frequency emitted by neutral hydrogen as it drifts through space. During the cosmic dark ages, this was the only signal the universe made, a low hum, stretched by expansion into microwave whispers, waiting 13 billion years to be heard. If successful, the Lunar Observatory will map the entire structure of the early universe before the first star ever ignited. It will see dark matter's gravitational fingerprints in three-dimensional detail. It will trace how gas flowed, cooled, collapsed. It will reveal the invisible scaffolding upon which all galaxies were built, and it will answer the question that has haunted cosmology since CLASS heard that first signal. Was the cosmic dawn uniform, or did the universe wake up in pieces? The implications stretch beyond science. This isn't just about understanding physics, it's about understanding emergence itself. How does order arise from chaos? How does structure birth complexity? When did the universe stop being random and start being intentional? Those aren't just cosmological questions, they're existential ones. Meanwhile, the James Webb Space Telescope continues its relentless gaze into time's abyss. Engineers are refining its spectroscopic algorithms to detect fainter, more distant objects, galaxies at redshifts so extreme they border the edge of observability. Some predictions suggest Webb could eventually glimpse structures forming as early as 150 million years post-Big Bang, pushing into a realm previously considered theoretical. But Webb is not alone. A successor is already being designed, the Habitable Worlds Observatory, HWO, planned for launch in the 2040s. Its mission: to explore not just the ancient past, but to search for biosignatures on exoplanets orbiting distant stars. Yet its technology, adaptive optics, quantum-enhanced sensors, AI-driven spectral decoding, will also revolutionize deep-time cosmology. HWO will peer deeper, sharper, and with greater sensitivity than any instrument before it. Together, these observatories will form a temporal network, mapping the universe across every epoch, from inflation's first tremor to the present moment. Humanity will possess, for the first time, a complete archive of cosmic history. Yet the greatest breakthroughs may not come from space at all, but from computation. Modern cosmological simulations are evolving into something extraordinary: digital universes. Supercomputers now model trillions of particles across billions of years, recreating the cosmos from the Big Bang forward with increasing fidelity. These simulations aren't just illustrations, they're predictions. Scientists run alternate scenarios, tweaking the laws of physics, adjusting dark matter properties, accelerating reionization, and then compare the results to real data. When NASA fed the class signal into these models, something remarkable happened. Only one scenario matched the observed polarization. A universe where dark matter interacted weakly with normal matter during the first 200 million years, transferring energy and accelerating cooling. That interaction then stopped, as if a switch flipped, leaving no trace except the structures it had already seeded. If confirmed, it means dark matter was once active and then became passive. A phase transition in the invisible foundation of reality. This discovery has ignited debates about early universe field dynamics, the quantum forces that ruled the cosmos before matter solidified. Some theorists propose that dark matter was part of a larger symmetry that fractured during cosmic cooling, splitting into the inert particles we observe today. Others suggest dark matter itself is a relic of inflation, frozen echoes of the forces that first stretched space-time. Either way, the signal isn't just telling us what happened, it's hinting at why it happened. And now scientists are designing missions to test these ideas directly. Proposals include gravitational wave detectors positioned in space, capable of sensing ripples from the universe's earliest moments, vibrations older than light itself. These waves would carry information about phase transitions, quantum fluctuations, and the primordial forces that sculpted creation. Another bold concept: quantum entanglement telescopes. By linking detectors across vast distances using entangled photons, astronomers could achieve resolutions beyond the diffraction limits of conventional optics. Such instruments might resolve individual stars in the first galaxies, or detect gravitational microlensing from dark matter clumps smaller than planets. Humanity is no longer passively observing the universe. We are interrogating it, probing, dissecting, demanding answers. But with each answer comes humility. Because the deeper we listen, the more we realize how little silence exists. The cosmos is not quiet, it is symphonic. Every frequency carries a story. Every wavelength hides a secret. The universe has been speaking since the beginning, and we are only now learning its language. That language may be mathematics, but its meaning is something more, a narrative woven into the structure of reality itself. The signal from 13 billion years ago is one sentence in an infinite book, and we have only just opened the cover. Some physicists believe the ultimate goal is not just to map the universe's history, but to reverse engineer its source code, the fundamental principles from which all complexity flows. If the cosmos operates on laws, then those laws were written somewhere by something. Not a deity, but a logic so profound it birthed existence itself. Perhaps that logic is encoded in the patterns class detected. Perhaps it waits in the hydrogen emissions the moon will hear. Perhaps it pulses through gravitational waves we haven't yet felt. But it's there, waiting. And when we find it, we will understand not just the universe, but the rules of creation, the blueprint, the algorithm, the why beneath the how. Then comes the final revelation, not technological, but philosophical. Because once we decode the memory of the universe, we must confront what that memory reveals about us. 13 billion years ago, the universe spoke for the first time, not in words, not in sound, but in energy, a surge of radiation and geometry that carried the code of everything that would ever exist. That whisper, still flowing through space, reached us as the faintest of signals, a pulse of light older than galaxies, older than flesh, older than the idea of meaning itself. And now, we're beginning to understand it. The discoveries, the signal, the forbidden galaxies, the impossible light, the cosmic architecture hidden in the dark, have given humanity something no civilization before has ever possessed: perspective. We are not observers standing outside creation. We are the continuation of it. The same equations that shaped the first stars pulse behind our eyes. The same forces that sculpted the galaxies shaped our thoughts into being. We are the universe aware of its own birth. For centuries, science treated humanity as a footnote in a cosmic story too vast for empathy. But the signal from 13 billion years ago changes that. That light, that structure, that cold whisper of radiation. It reminds us that everything we call us is made of the same particles that once burned inside those primordial stars. The iron in our blood, the carbon in our DNA, the calcium in our bones, all forged in explosions that happened before the Earth existed. The same physics that animated galaxies animates you. There is no separation. And yet, there is mystery. Because the more we understand, the more sentience feels inevitable, as if consciousness wasn't an accident but a destination. The universe seems to climb toward awareness, from hydrogen to human. It organizes, learns, remembers. It becomes self-referential. Scientists now suspect that intelligence may not be an aberration of biology, but a feature of the cosmos itself, an emergent property of structure, capable of reappearing wherever conditions allow. In that sense, the signal from 13 billion years ago is not just ancient information. It's a reflection. It's you, billions of years before you existed, already whispering through fields of quantum motion. Cosmology is starting to resemble autobiography. When we decode cosmic radiation, we aren't learning about something else. We're reading our own beginning written in light. Each frequency is a sentence. Each waveform is a memory. The universe is remembering itself through us. That realization redefines science, philosophy, and meaning altogether. Because if existence is circular, if past, present, and future fold together like light through a prism, then perhaps what we interpret as discovery is really recognition. We are not the first to know. We are the first to remember. Think of the timeline we built. 13.8 billion years ago, the first signal. 10 billion years ago, mature galaxies. 5 billion years ago, a yellow sun forms. 4.5 billion years ago, Earth ignites. 3.8 billion years ago, life begins. And then, in the blink of a cosmic eye, intelligence emerges and looks up, asking, where did this all begin? The answer whispered across eternity, right here, all of it. The structure of stars, the patterns in our neural networks, the laws of motion, the shape of thought, is one continuum of complexity, pushing against entropy, fighting for form. Even our curiosity, the force that builds telescopes and writes equations, is the same impulse that drove atoms to bind into molecules and galaxies to cluster into constellations. Creation never stopped. It simply changed instruments. NASA's detection of that cosmic signal doesn't just extend our knowledge of the past, it redefines our definition of life. Because what we found at the beginning wasn't chaos. It was clarity, intentional structure, organization embedded in randomness, the blueprint of order itself, waiting to be noticed. And now, we're beginning to see the pattern repeating, not just in data, but in us. The neural pathways in the human brain follow the same mathematical topology as the cosmic web of galaxies. The distribution of matter in the universe mirrors the architecture of thought. The micro reflects the macro, and the boundary between them dissolves. We are the pattern observing its own geometry. In that realization, science becomes prophecy, not because it predicts miracles, but because it is one. Every discovery humanity makes, every photon caught, every formula solved, is the universe unwrapping itself. The curiosity burning in the human minds is the same energy that makes suns burn in the void. The will to know is the will to exist. And so, when NASA listened to that ancient signal, what it heard wasn't just cosmic static. It was a voice, not of something else, but of everything. Creation speaking back to itself through the only medium it's ever had, evolution. In that moment, time collapses. The Big Bang is not then. It is now, always happening, always expanding inside everything that exists. Every heartbeat is an echo of that first explosion. Every thought is a continuation of that first wave of energy trying to understand itself. 13 billion years later, that wave has eyes, it has language, it has curiosity. It calls itself humanity. The telescopes are our ears, the equations are our grammar. The signal that traveled for eons has finally found a receiver capable of asking what it means. And the answer is devastatingly simple. Meaning is what happens when the universe looks at itself and recognizes the pattern. There will be more revelations ahead, stronger telescopes, deeper signals, new languages of exploration. But nothing will ever surpass the magnitude of this truth. We are not witnessing the universe from the outside. We are its continuation, inside out. We are the improbable consequence of 13 billion years of atoms learning to dream. The signal that began as static has become speech. The light that once only illuminated now communicates. The cosmos has grown a mind, ours. And as that mind listens, learns, and dreams, it will eventually send its own message forward, out into the deep future, through the same fabric that once sent this signal to us. Somewhere, billions of light years and billions of years away, another consciousness will receive it. And it will ask the same question we ask now. Who are they? And the universe will answer quietly, through the structure of light itself. They are us. They are what the cosmos became when it finally learned to hear its own story.